Welcome to week 5 of the class. Now we're going to switch directions and go from talking about basic statistical principles of inference to discussing the approaches we can use to actually select samples from a population. We're going to spend this lesson talking about some basic principles we need to keep in mind when designing a sampling survey. The field of natural resources is every bit as diverse as the methods we can use to sample them. Because of this, we will try to answer the following questions when considering the sampling approaches we cover, including which method is right for my objectives, what assumptions do we have to make, how efficient will it be compared to other approaches, how strong are the inferences by collecting data via this method, what are the limitations with each method. In order for us to make informed decisions as natural resource managers, we require accurate and representative data. However, low-value resources, or resources with high sample unit costs, often receive lower sampling intensities. Something we should keep in mind moving forward with designing sampling protocols is Occam's razor. Entities must not be multiplied beyond necessity. The simplest techniques and solutions are often the best. However, these simplest techniques are often the most abused. A simple fact of life and management is that nothing comes for free. We must consider the cost of sampling against the potential gains from the information obtained. If we invest $10,000 in sampling but learn nothing new, was it worth it? An important aspect of designing sampling strategies is to take advantage of prior information about the population and knowledge of the ecosystem. This can mean using old inventories, soil surveys, and remote sensing data, all of which can help limit sampling costs when used appropriately. We are trying to balance the cost of sampling with the benefits of measurements, meaning that if we have a high cost to measurement ratio, taking extra measurements may hit a point of diminishing returns earlier than if the ratio is low. The thing to take home from this is that the benefits of an inventory are a function of its purpose, precision, and cost. When it comes to generating a representative sample, it is not a trivial challenge. By this, I mean a sample that accurately reflects the characteristics you are trying to capture from the population. Because of this, the quality of a sample is as important as the sample size. As we move through the next few weeks of the class, it should become clear that all the designs we talk about are just different ways of selecting which parts of the population to measure, and that this is a critical step. If we were conducting a survey of all voters and we utilize a protocol that systematically excludes voters younger than 30, the sample would be worthless. As we have seen, being able to invoke probability theory is an immense benefit to us, and the easiest way for us to do this is by using random sampling, which ensures we have a representative sample. Now let us recap some of the differences between probability and non-probability based sampling. Although we have discussed both of these approaches, there are a couple of key things I want to drive home. Probability-based sampling relies on each sampling unit having a fixed, known chance of being selected. We obtain this by taking a random sample. Conversely, non-probability-based sampling does not have this constraint because it utilizes non-random sampling, where sampling units are selected out of convenience. Since we are utilizing a random process of selection in probability sampling, we can assume the following is true. This process helps to reduce the possibility of bias, and the statistical inference can be made about the larger population from the sample. When conducting probability sampling, we have a range of approaches to select from, including simple random sampling, stratified sampling, cluster sampling, and systematic sampling. In non-probability sampling, sampling units are selected through a subjective process that causes the following to be true. The process has an inherent level of built-in bias. The conclusions drawn by the sampler cannot be inferred from the sample to the whole population. Though biased, purposeful, or judgment samples can provide valuable information, particularly in the early stages of the investigation. The types of samples this relies on utilize the approaches of convenience sampling, quota sampling, judgment or purposeful sampling, and snowball sampling. Moving forward in this course, we will exclusively focus on probability sampling, and now look at the things we need to ensure for a probability sampling process to be successful. An idea we will come back to, but that is important to consider before designing a sampling process, is that the study's objectives need to be clearly defined and include details about what information is required, what precision is required, and why the data is being requested. Such a statement might look something like an inventory to estimate standing volume to within 10% of the total volume per unit area and within 12% of the total value for the stand alpha, but both at a 95% confidence interval. The first step in designing any sampling plan is defining these sampling objectives. Once we understand our objectives, we can begin to determine the number of samples to be taken and how samples will be selected or located in the population. As we consider these two pieces of a sampling design, there are three general requirements that need to be considered. First, we need to have a random or unbiased sample. If your study does not contain some manner of random sampling, you cannot determine the probability of selection and therefore cannot make statistical inference about your population. The second thing we must consider when setting up a sampling design is the idea of interspersion. This means your sampling units should capture the variability of the target population. Sometimes this is interpreted as meaning that the sample should be spatially spread across the area of the population, but in reality, it means the sample units should capture the possible values that the population variable can have. Succeeding at this ensures that we have a representative sample and that we will have strong inference about the population. A thing to keep in mind is that in natural resources, this means we have to proportionally sample things at the edge of the population that might differ from the rest of the population due to differences in their environment. The final requirement of a probability-based sampling design is the necessity of sample independence. This means we need to ensure that our sampling units are selected in a way that they are not influenced by sampling units that have already been selected. If we think about this from a pure statistical sense, it means you need to avoid spatial and temporal autocorrelation or oversampling so that one sample is not being informed by the one before it. In natural resources, we generally consider this to be locating our plots so that they are sufficiently spaced apart that we are not remeasuring the same information. Typically, we accomplish this by utilizing sampling without replacement, which we will talk about in the simple random sampling lecture.